distinguished lecture. It's my pleasure to introduce Keshav from Waterloo University. Keshav has had an amazingly varied and frankly distinguished career in networking. He received his PhD from Berkeley with Domenico Ferrari in the early 1990s. And from Berkeley went to Bell Labs, where he, again, had a distinguished career there. From Bell Labs, he tried his hand in academia with teaching stints at, he taught a little bit at Columbia, as I recall, and finally ending up at Cornell. Then, having done industrial research, he became, and tiring a little bit of, I think, academia, he tried his hand as an entrepreneur and founded a number of startups. The one I remember best was Ensign, which is still with us today in some form. And from Ensign, he went to his current position at Waterloo, where he currently is a Canada Research Chair in tetherless computing. Keshav has won an amazing number of awards over the years, so many that I can't even, it would take me the hour to enumerate them all, but let me just tell you about one that I think is just tremendously impressive. In 2006, the ACM Special Interest Group on Communications, SIGCOM, initiated an award that was called the Test of Time Award. It's sort of a Hall of Fame thing, where they would look back 10 years and recognize those works that were still highly relevant, still highly cited, and still widely read. And so in 2006, they had a lot of catching up to do, so they looked at this period from 1969 to 1995, so essentially a 25-year period. And in that 25-year period, they picked, I think it was about 15 papers or so for this inaugural test of time. 2 of those papers were Keshav. So out of 25 years, 2 works came from Keshav. And I believe the only other person who was so recognized was some obscure person by the name of Lenny Kleinrock. So it just shows you the company that we're keeping here. And despite all of this, all of these fabulous achievements, the other thing that's amazing about Keshav is he doesn't own a laptop, and so I actually have to lend him my laptop for him to give this talk. So we're delighted to have you here. With further ado, Keshav.
Thank you very much. Thank you for coming. Thank you very much. Thank you for coming. I hope to convince you by the end of this talk that you're in the wrong research area and you should all be working on smart grids. So the goal here is to really tell you about how the internet can green the grid and to show you some of the interesting problems that come around here, and hopefully you can use the expertise that you have in addressing these problems. But whenever I go somewhere, people ask me, where the heck is Waterloo anyway? And so what I decided to do was to give you a small geography lesson. This is the US. That thing up there is Canada. Please note that some part of Canada kind of sticks down, stabs into the US in that part. And if you focus on this part over here, that part is this big triangle that comes down over here. And it's between these 3 Great Lakes. And in this section right here, if you focus in, you are in this big chunk over here. You see this town called Kitchener. And right next to Kitchener is this really itty-bitty little town called Waterloo. And that's where you have the University of Waterloo. And I live right there. OK, so that's Waterloo. And just to give you context again, zooming out, it's Kitchener. And then that's the triangle that sticks out there. And that's the United States. So now you know where it is. We're about an hour southwest of Toronto. And this is a typical Canadian of indeterminate sex, about 9 months out of the year. Between May and August, we wear T-shirts, and the rest of the time, it's like this. So I'm glad to be here. OK. Strictly speaking, it doesn't look like that. This is what the university actually looks like, and that's my computer science department. And this is what downtown actually looks like. And right now, it's 11 degrees centigrade, so it's about the same as here. We do have a fair, we have the home of Wat4 for the older people around here know what Wat4 was. Maple blackberries from across the street from us. Engineers Without Borders started at Waterloo, and the Perimeter Institute, which is for theoretical physics, is at Waterloo as well. We have about 25,000 students, about 200 faculty members in mathematics alone, 17 computer science, and computer science has 2,000 undergraduates, so slightly larger than the department over here. OK, so now for the quiz. This is about the end of the day, and most people are sleepy, including perhaps me. And just to wake you guys up, I'm going to show you 7 photographs. I'm going to ask you what's common to them, right? So people in the other locations, feel free to speak up as well. So here's the first one. It's a boy next to a dike. It's a sculpture in Holland. This is a famous work of fiction. No, sorry. It's a famous work anyway by Karl Marx. This is the map of Europe just before the First World War. This is actually Len Kleinrock standing next to an interface message processor. This is a picture of the Alto. And this is the Berlin Wall just before it came down. I guess the day it came down. And this is an avalanche just about before it went down. So what's common to all these pictures? Yes. So the avalanche, the Berlin Wall, the Alto, the imp, the map over here, capital, and the part of the thing. So anybody want to take a guess on this? Yeah.
You can't stop them.
Okay, that's good. Something more than that? Anybody from the other?
They're all failures?
Beg your pardon?
Are they failures?
Failures. Yeah, you can think of them as systems just before a big failure or a big change. Okay. The way I draw it is like this. Systems over time sort of accumulate what you can think of as potential energy, which I'm showing on the y-axis. On the x-axis is time. And small increases don't really cause any problem, and they come down again. But once it reaches criticality, enough snow is piled up to the top of the mountain, then even a small little push is going to send it all the way down. And that's what happened in World War I, where one assassination of one archduke caused the whole continent to go up in flames. That's what happened with the wall, the Berlin Wall. And my claim is this is what's going to happen to the smart grid. So I'm going to try and explain why that happens. And a more interesting thing is my analysis of this is that a system which has got built into it internal contradictions along with external pressures, okay? And when there's a small technological push, can suddenly change phase. It can become completely different. And that's sort of what I think the grid is going to become, which makes it really a big opportunity for people who want to work in this area, because you don't want to work in a system which is steady state. It has no changes happening like the internet, right? Because everything is just where it's always, everybody's used to it. It just kind of works almost all the time. But if you are in a system which is changing, then you have an opportunity to contribute to the change, hopefully in a positive way. So before I can do that, I need to tell you what the grid looks like. So I'll have 2 slides to tell you what the grid looks like, the grid for dummies, if you will. This is what the grid looks like. Basically, we have on the left some sources of generation over here. For example, a coal plant, a nuclear plant, and hydroelectric plant. And these generation sources are connected to transmission, which looks like a bunch of lines, transmission towers. And the transmission is connected to what's called the distribution, which is this stuff over here. And what I'm showing is a distribution in more detail. It's a substation over here. And this substation talks to pole top transformers. If you look around, as you walk out, you'll see on tops of poles something about this big, and that's a pole top transformer. And from the pole top transformer, you have distribution to different houses. Similarly, pole top transformers also go to commercial buildings. Okay, so that's what it looks like. So the fundamental constraint in the grid today is really that generation must match load all the time. So if I turn on a light switch here, some generator somewhere has to pump in more electrons to match that. So it's a constant game of matching the load as it goes up and goes down, and that's what keeps all the power systems engineers quite busy matching this. Okay, that's in 2 slides pretty much what you need to know about the grid. Okay, so there is a crisis that's coming over here. What I'm going to show you is the reason why there's going to be a crisis. It starts out like this. We have an ossified technology. The technology that's in place today is stuff that was put in not by our parents or grandparents, but by our great-grandparents around between 1890 and 1920. It's ossified. And on top of that, it is inefficient. We have problems with rising energy prices. We have problems with cascading failures. So one component fails, and it can cascade all over. We have problems with energy security. The energy is coming from places you may not necessarily want to go on a vacation or invade, as the case may be. There are economies that are growing, and so they need more energy. And the carbon footprint of all these energy is rather large. So with all these, we essentially see this energy buildup, okay, or the potential buildup over here, so that one small technological push can bring it coming down. So in the next few slides, what I'm going to show you is sort of why this is happening. So let me just start with the ossified technology part. If Edison, who's shown over here, were to go to a coal plant, which is a modern coal plant today, with 1 day's training, he'd probably be able to run the show, because he kind of knows where everything is. It's the same old thing. It's the same generators, the transformers, the transmission lines. Everything is pretty much the same. Put him in the data center, and he wouldn't know what the boxes did, or what the wires did, or what was happening. He would need years and years of training just to figure out what was going on. So that tells you the difference between old technology in some sense and new technology. It's radically different. This graph is a little bit of an eye chart, but I'll sort of walk you through it. This is a chart from Lawrence Livermore National Lab, and it's showing on the left-hand side over here a bunch of different sources of energy: coal, wind. Coal is gray, natural gas, geothermal, wind, solar, petroleum, things like that, and different places where it's consumed for electricity generation, which then is used for residential or commercial, industrial, or transportation. Okay, so it shows where all the flows go. It's a really nice chart. It's really worth looking at in more detail. And I'm going to focus on just one thing, which is that the total amount of energy used in the US in 2008 is 99.2 quadrillion BTUs. So it's 99 somethings or 100 something. So everything can be viewed more or less as a percentage. So if you look at it, basically of all the electricity generation, which is 40, 27 of it is rejected, waste energy. Okay, so 27 of 40, about 2/3 of all the energy used for electricity generation is wasted. Okay, and you say, that doesn't make sense. Why is it wasted? Well, the reason it's wasted is because the way electricity is made is you take water and you heat it up, and you put hot water through a turbine, and it spins, and then you cool it down again. If you've ever seen a nuclear power plant, you see these big towers, right? Those big towers are not where the electricity is being made. Those are cooling towers. After the water is hot, it needs to be cooled down before it goes back into the river, otherwise the fishes die. So those enormous concrete structures practically show you how much energy is being wasted. That's all wasted energy over here. It's the heat energy that's being wasted right there. Okay. The second problem is that coal, this black thing over here, is responsible for, coal and natural gas are together responsible for about 2/3 of all the electrical energy. So you say, I want to be green, I'll go buy a Prius. So you go buy a Prius, you buy you plug in hybrid car, you plug it into the wall. You may as well put coal and drive the car on coal, okay? Because that's really what you're doing, okay? All that coal is really what's driving your car. So it's not just enough to buy a plug-in hybrid electric car. You got to figure out what to do about this stuff over here. So that goes to the carbon footprint. Now here's the inefficiency problem. In addition to the wasted heat, this is testimony from Phil Giddis from the Massachusetts Department of Energy. Said 15% of the generation capacity in Massachusetts is needed fewer than 88 hours per year. So 88 hours is like 4 days. Okay, it's upper bounded by 4 days. So 361 days out of 365, 1 in 7 power plants is just sitting there doing nothing. Okay, it's just doing nothing because on the 4 hottest days of the year, you need to turn it on. So you just build it, and it's doing nothing, and that's what you do. And so that basically is inefficiency. So 1 in 7 is quite a bit of capital cost that's been gone into the system. The rising prices, I'm just showing you 2 prices. One is over here is the price of natural gas per 1,000 cubic feet. And you can see it's basically in constant dollars, it's rising over here. Coal, interestingly enough, was going down, and then when you had the fuel crisis in '73, it kind of shot up, went down, and then it's up again. But overall, the trend seems to be going up because of the demand from other countries, especially from China. Okay. So this is the energy security part. These are the top 10 energy producers for oil. Now, it's not, the US does not actually burn oil for electricity. It mostly burns natural gas and coal. But just, it's interesting to see which are the top 10 oil producers in the world. Other than Canada, all the others are countries which are not very friendly to the US for the most part. Iran, Iraq, Kuwait, places like that. And Canada, well, you have to invade us at some point, I guess, to get all the oil, because Canada is the number 2 oil reserve country in the world, $180 billion of oil. Okay, so, all right. And by the way, all the oil in Canada comes from extremely dirty tar sands, which they prefer to call oil sands, but I call it tar sands. It's Alberta. Okay, it's all done by injecting high-pressure steam, and so it's a really messy process, and you really don't want to do much of it if you can avoid it. cascading failures. This is two pictures. This is the day before the failure of August 2003, and this is the day after, day off. So you can see what happened to the lights from viewed from space. You can basically see big chunks, especially New York State, and this area just went out. Toronto, which is over here, is completely dark over here. So that's what happens when you have cascading failures. It really affects what's going on. So again, that's a feature of our system today. And the generation gap, I don't mean between me and my kids, but between the countries on the left shown over here. So this is the terawatt hours generated in the US, 4,000 terawatt hours. China was 3,400. This is in 2008. Now in 2010, actually China took over from the US. It actually generated more than the US. I didn't have numbers for the rest, so I didn't put it in. India is at 723, Canada is 620. Look at the per capita though. That's where the numbers get very interesting. US is at 13 megawatt hours per capita per year. China is at 2.5, India is 0.6, Canada is 18. So this is a lot of it. Well, I don't know why why the Canadians are so inefficient, but at any rate, these two numbers are going to go up. There's no question about it. And where is it coming from? It's going to come from coal. Okay, it's going to come from coal, which means that they're going to put in more carbon dioxide into the air. So this is really bad for the essentially carbon dioxide load of the environment. So these are the stresses and strains unto which the system is subjected. We have prices going up. The system is not that stable. We have people who want more electricity, but then are they going to build it the same way? One question you could ask is, should China and India build the electricity grid in the same way that the US and Canada built it? Okay, or can there be better ways? Perhaps to set the question in context, you could say, should China and India have built the telephone network the way the US and Canada built it, or should they have used cell phones? And the answer is clear. When there's better, newer technology like cell phones, use it. It's actually much easier, much more convenient, much more appropriate. So why should these countries build the grid the same way as they built over here? So that's I think, certainly an interesting question to ask. All right. Now, there has been a technological response to it. These are the technology push factors. I'll go through 4 major ones and 3 minor ones. So the first one is high voltage DC and superconduction. These are transmission line technologies. And what they allow you to do is to link up very large distances with very low transmission losses. For example, you could link up the Sahara Desert to Europe, okay, with a superconducting link across the Mediterranean. And that will allow you to get solar energy from the Sahara to power Europe, and actually there are people trying to do that. The other thing is renewables. There's a lot of investment in renewable energy, solar, wind, geothermal, tidal. The main point of these is that they are distributed. So you generate the energy where you use it, so you don't have to worry about energy security. You don't have to worry about energy prices. Actually, the prices of these things are coming down, not going up. At least solar is coming down. These are clean. They have essentially no carbon footprint other than the cost of manufacturing. That's a one-time cost, and then for the next 25, 30 years, you don't have any footprint. Storage technologies are a very big deal. If you remember, the big fundamental constraint in the grid was generation equals load. But here with storage, we can break that equation. And the reason we can break it is because of plug-in hybrid electric vehicles, which are really batteries on wheels. Okay? With this, what happens is that we can store solar energy at night and use it. Or if there's a peak, the 15% of the time of the capacity that was kept for hot summer days, you could meet that perhaps from the cars. Okay? And when you have PHEVs, you get storage, plus you get mobility, so you can move lots of energy. How much energy? Okay, typical PHEVs have about 20 kilowatt hours of storage. That's about how much a typical American home uses in one day. So in other words, if you have a car in your garage and you have a failure and the whole grid goes down, for that one day, you can actually be perfectly fine. You won't notice anything. That's how much storage you have. It's quite a bit. Okay, it's pretty substantial. The nice part is the consumers are buying it for you. And if you're the grid operator, consumers are putting down $10,000, $20,000, $30,000 to buy batteries for you. Okay, that's a great deal. Okay, so there is certainly a good idea to try and use this in some fashion. In addition, we're having technology for communication, like basically internet or cell phone type communications. There's technology for bidirectional energy flow. So if you generate electricity at home, you can actually push it out again. So it's not just one-way flow, but it's two-way flow, as well as advanced metering infrastructure or smart meters, which allow people to know how much energy you're using, when they're using it. And if you don't even know how much you're using, how can you reduce it? How can you control it? So this is very important, and it's basically happening all over the world. IBM has installed more than 30 million meters, smart meters around the world, and is putting up. In Ontario, we're going to have 1.7 million smart meters installed by the end of this year. So in the next 6 weeks or so, we'll have 1.7 million installed. My house is a smart meter, for example. Okay, so these are all the technology push factors, and I put these and circle these as yellow because I think a 10x improvement in any one of these four can completely change the way that the grid looks like. Okay, but even not a 10x, even a small x and a small factor improvement in any of these four things or all of these four things is the small amount of push needed to completely change what the grid looks like, and that's really what people have been calling the smart grid. Okay, so if the smart grid comes about, this is one vision of what it would look like. If I take the same picture again, what I've shown instead of coal and nuclear is wind and solar, and the hydro is still clean, so we'll leave it there. At the substation, I put in storage. That's actually a hydrogen fuel cell. And at each home, you have cars, a plug-in hybrid car, you have wind and solar, and you have bidirectional electricity flow going back into the grid over here. And this is sort of my view of what the smart grid looks like. Yeah?
So with regard to the cars, are you proposing that you can use the power stored in my car to drive my lights?
Yes.
What happens when I want to go somewhere next day?
Then the lights go off. I mean, seriously, you have to be careful about that. And so you may have, in addition to your car, some lead-acid cells for your lights. People do that. People actually put in UPSs, which is nothing more than car batteries, but not in a car. So yeah. There's no magic here,
The consumer paying for it. We are paying for it because we get a car, not because we want to help the grid.
That's correct. You're paying for it because you want the car. And if it turns out that you can use it for other things and make money on it, for example, by selling the energy in your car to your neighbor, then why not, if you don't need it, right? So this is another vision of the smart grid. So basically, I'm trying to show you that I'm not the only person thinking of smart grids. This is a picture from a company called Trilliant. These are the guys putting up smart meters all over Ontario. And they've actually built a multi-hop wireless Zigbee mesh, which has a house-to-house hop from the meters to a pole. And from the pole, it goes to a pole top. And then that goes multi-hop to the headquarters over here. And what these guys can do is that they can then do time-of-day billing, or they can send you control signals back saying, turn off the AC now because it's a power outage is going to happen otherwise. And there are wind and solar and all the other things as well. This is from Panasonic Research. Same thing. They have wind, they have solar, they have plug-in cars, plug-in hybrid cars. They have the house solar panels, power substation, power plant. Here's a picture from the Department of Energy. You see, you get the picture. It's the same old thing. You have solar, so you have wind, you have solar, you have the plug-in car, both at home and at work, and then you have, all the other ingredients. So there seems to be a convergence of opinion on how to solve the crisis. Let's go for distributed generation. Let's use renewable energy sources. Let's have smart meters. So all the other things I told you about. And so you can say, okay, great, we're done. If you know what to do, let's go home. Everything is taken care of. But that isn't the case. Okay, there are lots of problems. Okay, so let me just walk you through some of them. And this unfortunately is a text-heavy slide, so just bear with me. So the first thing is that the grid today has generation sources about 1,000 or so. The US has about 1,000 big sources. Most countries have between 200 and 1,000. And I'm talking about power plants, big hydroelectric plants, thermal plants, nuclear plants. There's not that many. When you have lots of solar cells all over the place, everybody puts one on the roof. You have millions of sources, and coordinating them becomes quite difficult. Okay, it's not something people are used to doing. More importantly, these are stochastic, variable sources. If the sun, if the clouds go across the face of the sun, the solar output drops by 95%. If the wind stops blowing, your wind output goes by 100%, and every night your generation source goes away. Your solar source just goes away, right? So these are variable sources. And so you have to worry about how do you model that. It's not like you turn on a coal boiler and you get steady 5 megawatts from it all the time. The renewable energy is coming from wind, tides, and the sun. So you need places that are where there are a lot of tidal ups and downs that have a lot of sun and a lot of wind. In other words, it's hot, windy, and it's not places you want to live in. So all these solar energy, these resources are mostly in places nobody wants to live in, because it's just too damn hot to live in the Sahara Desert or on top of a mountain top where it blows all the time. So you have to backhaul the energy back to places people actually want to live, and that's very expensive. Okay? To put in the transmission lines, put in the transformers, to put in the maintenance, all that stuff becomes very, very expensive. You must have heard of T. Boone Pickens, who wanted to put up all these wind plants all over Texas. Well, it failed. It failed because backhauling all the wind energy back out of Texas into California was too expensive. Okay? Even he, as a billionaire, couldn't afford it. So we need to figure out something cheaper than that. The flows in the current grid are one way. You know, the grid can be viewed as a content distribution network, which is always playing the same movie called electricity. You know, keep sucking the electrons down from the generators. Okay, just like you suck down the YouTube videos, you suck down the electrons all the time. Now what's happening is that it's not just content you're sucking down, you're actually putting content out again, the bits up again. So all the diodes are pointing the wrong way, basically. You need to send stuff back out again. You need meters in both directions. So it's a non-trivial amount of work to do that, design the power system the proper way. Now, anybody who has a Wi-Fi access point in their garage has become an ISP, whether they like it or not. Okay? Any neighbor who wants to can get access to them. They're an ISP, they provide internet service. Now, of course, mostly deny service to them. But anybody with a solar cell on the roof is a utility player. They're providing electricity, right? So how do you write contracts with them? You know, how do you make sure that they don't drive the car away when the grid needs the vehicle? Okay, what do you do? So it becomes a sort of legal issue over there. In face of all these, you have to maintain reliability. People expect the grid to be up 99.999%, the 5 nines that they want to have. How do you maintain reliability? In addition, we have other problems. You know, if you want people to turn off the ACs when it gets hot, what incentive do they have to do it? You know, they just want to be comfortable. Why should they turn it off? What happens if somebody hacks into your meter, or worse, hacks into the nuclear power plant and decides to have some fun or not? Security is extremely important in these cases, and the power systems people, generally speaking, are not experts in internet security. When you introduce storage over here, everything changes. The fundamental equation of generation equals load changes. The thing that storage may be on wheels and moves around changes. And even control loops, where you say make a change and you expect the reaction to happen right away or the response to happen right away, changes because now you have storage, which adds delay. So all these issues come up, and modeling and dealing with storage becomes quite a difficult problem. The other problem is now the variable demand. So we have the storage, the sources being stochastic, so the sources go up and down, but the demand also goes up and down. And the reason it goes up and down is because in many cases people introduce pricing to do that. So you could say energy becomes cheap at 9 o'clock. Well, what happens is that at 9 o'clock everybody turns on their dishwasher or their dryer, and so you get a load spike, okay, because of variable demand. So you not only have to control things, but you have to control the reaction that happens because of your control. So it gets quite difficult to model that. And all this has to be done with systems that are 100 or 120 years old. Okay, everything out there, you can't just go off and replace it. Whatever is there, you have to work with it. So these are the problems in there. And in a nutshell, what you can say is that the grid, because of these changes, is going from a relatively static, predictable, stable system, you know, kind of a thing that you can understand, with the loads are inelastic, mean they don't change, and a few points of control, to a highly dynamic, unpredictable, potentially unstable system, okay, with elastic loads and millions of points of control, okay. And given this, no wonder the operators look like this. They just don't know what to do. You know, if you have too many cars plugged in on the same side of the street, the transformer is going to explode, okay, because of unbalanced phase loads. You know, the government on the one hand says, turn off your coal plants. On the other hand says, you must buy electricity at 80 cents a kilowatt hour, and which is way more than you can charge for electricity, so you have to absorb the losses. And everybody wants reliability, and everything is changing under you all suddenly. So this is pretty accurate. In fact, they're so scared, they're even willing to talk to universities. It's amazing, okay? Unlike ISPs who are perfectly happy, you know, to make money as they go along, doing whatever they're doing, the grid operators are willing to talk to us and really want help from us, which puts us in a rather interesting position of having somebody to listen to all our talk. Okay, so so this is where we are, and the thing that makes it interesting for me, at least, that this, a highly dynamic, unpredictable, potentially unstable system with elastic loads, millions of points of control, is exactly a description of the internet. Okay, it is exactly this. Okay, we have no idea what video on YouTube is going to get popular. We have no idea who's going to hit which website with millions of points. It's very elastic. You can delay nodes, millions of points of control. This is really what the internet is. So my hypothesis is that what we learned on the internet can be used for the grid. Okay. So in fact, I think that the green networking research that's happening today is not being ambitious enough. It says, well, let's reduce electricity use. If a router isn't being used, just turn it off. Okay, that's basically what they're saying. But guess what? All of IT, all servers, all routers only use 1.5% of energy in the US. Okay, heating and ventilation uses 40%, for example. So if you do get all of this right, you're only touching 1.5%. It's in the noise. Okay, so it's not that it's nice, but it's not enough. Similarly, using the internet as a communication overlay, that says I can get bits from your smart meters to your to your company headquarters. Fine, okay, but it's not really exciting. What I really think is exciting is to change the way the grid itself is structured, okay, by using internet concepts, okay, and I'll kind of be more precise about it in just a minute. So that's the hypothesis, and for the next, I don't know, 5, 6, 7 years, I'm hoping to work in this area, and I'll show you some specific details towards the end of this talk. So in order for all this to work, it's essential that the internet and the grid have some similarities. They have to be sufficiently similar they can transfer ideas from one domain to the other. So let me show you some of the similarities. This is an interesting one. They're both vast and they're both historically similar. Okay, they both started out as bottom up. So the way the electrical grid started was somebody would get a diesel generator or a hydro generator, and they'd say, I can run my lathe from this, or I can run my drill from this, I can run my press from this, and they do that. And eventually they say, look, if my water supply runs up, if I'm on the grid, I can get energy from my neighbor, just like in the LAN. You can connect to each other. But once it got big enough, you had a top-down approach, and then you wanted to have national guidelines on connectivity and on grid connection, and that's what happened. The same thing happened with LANs and WANs. Basically, each LAN was done individually, and then the internet was really an internet, a connection between existing networks, the wireless radio network and the wired network that was in the Bay Area. So I don't know, I just put in some names of pictures of some of the founders. Maybe I should wake you guys up with some more. So do you know who these people are? So who's that? Anybody know that famous person? Tesla, right? That's good. This one is, yeah, you already saw that. Good for you. This one most people don't know, but any guesses?
What?
So, huh? What? No, it's Westinghouse. So he was basically did the AC transmission, and he employed Tesla. Tesla was he was a genius. Okay, these are, in my opinion, the founders of the internet. I may be wrong here, but okay, this is Vint Cerf, Bob Kahn, and Len Kleinrock. Okay, so all right. So I think historically these are the founders. They don't look like each other actually, but anyway, I just put it in. They both match geographically distributed demands with distributed generation. Okay, to kind of visually show you this, I'm going to show you the grid for the US. This is the grid. This is what it looks like at the high level. And the different colors correspond to different transmission line capacities. It's not important what they look like. But look at where the dense zones are. There's a density over here. There's density along the East Coast, along the West Coast. This is from QIDA. It shows the IP addresses in the internet, in the US, I'm sorry, IP endpoints. And you can see pretty much the same kind of distribution of IP endpoints. And it's not surprising at all. People want information. People want electricity. And the grids go where the people go, where the people live. This is where the cities are, basically. So they both, therefore, meet geographically distributed demands for energy and information with distributed generation of energy and information. Okay. Data centers are the generators of the internet. Okay. So they're both heterogeneous, they're both critical to society, and they're both ossified. Okay. The internet really hasn't changed in the last 30 years. Okay. One could argue that since 1973 and the TCP/IP, there's been a couple of tweaks to TCP to make it more efficient, but that's about it. There hasn't really been much change since then. Of course, the grid hasn't changed since 1920 or 1910. You can pick a date. So they're both equally ossified. They're both hierarchical, actually. You may be surprised to see this, but I'll show you pictures in just a minute. The electrical grid is actually a mesh at the core, and the axis is a tree. And the reason is because in the core you want alternate paths. You're willing to pay big bucks for alternate paths because you don't want any city to be cut out because it was, didn't have an alternate path from a generator. But at the axis, you're trying to save money. So you don't care about cutting off this building if you have to. So you build a tree to this building, but the city of Raleigh will have access to a mesh. So this is the ISP, a mid-size ISP. You can very clearly see the mesh-like core and the tree-like edges. And here is the Kansas electrical transmission grid. The blue stuff is the core, it's mesh, and the green stuff is axis, and it's by and large a tree. You can sort of see where the tree is over here. Okay. So we get a similar kind of topology because they're driven by similar economic constraints. The APIs for both are very simple. This is the API for the grid. Okay, plug and play. Okay. And you may think I'm making a joke here, but it's not actually that stupid. As long as you're willing to put a plug on your appliance, you can innovate on toaster design all you want and still use it, okay? Because the grid supplies, the same exact thing. It has 60 hertz or 50 hertz, 220 volts or 110 volts. You pick the parameters over here. You know what's going to come. You can innovate all you want on this end. In the same way, IP is the simple API for the internet. Okay, everything, as long as it speaks IP, goes through. Okay, I'm not talking about spam filters and all the other fancy stuff we've done, but at the heart of it, the internet is a very simple API. There are differences, though. Okay, the biggest difference is the electricity has no headers. Okay, so if I want to pick that one light over there and they say, okay, I want to send electricity from that light switch to that one light, but not any of the others. I can't put a header on it and say, okay, you light bulb, turn yourself on, all the others match themselves. Oh, that's not my address, I'm not going to come on. It doesn't work that way, no headers. Okay? But if I have a bus on which I put an Ethernet header, no problem, I have headers. So I can't have any type, I can't have any destination. So I can't sit here in this building and say, I only want wind power electrons to come in here. I'm going to get whatever electrons want to flow here because of Kirchhoff's laws. I can't route. Okay, all I can sit here and get whatever electrons come to me. So this is a big difference. You can't plan it out, you can't provision it, you can't route it the way you can do in the internet. Okay, so you have to be careful about that. The internet is primarily two-way. Okay, it can support two-way, whereas the grid is primarily one-way. It's still primarily one-way. So we have to worry about, there are no acknowledgements, okay, in the electrical grid. You just get down electricity. You don't act your electrons one by one. Got electron, done, it doesn't work that way. So we can't do packets. So you have to be careful about that. The other thing is a bit interesting. Let's say I have a link between Chapel Hill and Raleigh, and it's at 10 gigabits, and I want to go to 40 gig. What do? I just swap out the lasers, I put in more lambdas, and I'm done. Okay, the fiber optic remains the same. On the grid, electrical grid, it's not the same way. If I have a connection with this, it has a certain amount of capacity. If I want to add more capacity, I have to put more copper, more wires, more transmission towers, which means that, and it's expensive. So which means that if you're given a particular topology, you really don't have the opportunity to change the topology very much. Okay, you can add a few transmission lines here and there, but you're talking billions of dollars to do anything more substantial than that. Finally, there is this difference in the sense that the grid has practically no storage. Okay, the total amount of storage in the grid, most of it today comes from what's called pumped hydroelectric, which means you pump water up a dam. So the wind blows at night, the turbines are spinning, you have the electricity, you don't know what to do with it, you run a motor and you push the water back up the dam. The next morning when you need it, you have water. So you have two reservoirs and a pump in between. And about 2% of electrical generation in the US can be stored in this fashion. It's pumped hydroelectric, but it's not very much. So, and batteries are not quite the same as DRAM. They have different charging and discharge characteristics. And if you charge and discharge them a few times, basically they give up. You can do it about, depending on how much you discharge, between 1,000 times and 1,000,000 times, unlike DRAM, which you can charge and discharge to your heart's content. Finally, the cost of storage is in the ballpark of $500 a kilowatt hour. Compare that to the cost of generation. It's about 7 cents is what you pay at the end point for generation, for consumption, 7 cents a kilowatt hour. The generation cost is typically about 2 to 3 cents a kilowatt hour. Whereas to store that 1 kilowatt hour takes you $500. It's really quite expensive. So we can't just throw storage at the problem. It's too expensive right now. So these differences have to be kept in mind in terms of designing things. OK. So I'm going to now change gears a little bit and basically talk about 3 research topics that my group is working on. And I'll talk about how these are all 3 topics are basically in the area of using internet ideas and applying them to the smart grid. Okay, so we don't want to work on areas that are only smart grid, only the grid related, because we don't know power engineering very well. Okay, so the first one is stochastic modeling. So the insight here is that when you look at solar and wind, they're varying. This reminds us very much of video sources which are variable bit rate. So we can think of these as variable energy rate sources. Okay, so and electrical loads are also varying. Okay, they go up and down. This can be viewed as sources with negative packets coming in. Okay, so if I say I'm generating a variable bitrate stream, but if I think of packets as being negative, I can think of them as consuming variable packets in this way. Okay, and the negative part has to do with the exact differential equation that governs the system, and I can talk more about that offline. But with this insight, we can now answer this following question, for example. Can renewable energy be made more reliable? So I have, let's say, 1,000 houses, each with a solar cell on it. And I want to ask the question, can I use it for base load? Which means I want to use it for energy that's supposed to be on all the time, which could be, for example, some kind of a refrigerator. Well, not a refrigerator, but some light that needs to be on all the time, for example. We can view this as saying, what is the probability that the sum of these variable sources exceeds a base load with probability greater than 0.99999 by reliability constraint? And for those of you who study teletraffic theory, this looks awfully familiar. This is, in fact, the exact same equation that you study in teletraffic theory, where we take a sum of variable sources, often modeled as on-off or Markov modulated Poisson sources, and we compute the probability with which it exceeds the threshold, and this is then defined as the network reliability constraint. Okay. So we can actually use teletraffic theory over here. And the nice thing is we don't need to worry about the packetization to fluid approximation. It is a fluid already. So that works pretty well. Plug-in hybrid electric vehicles are essentially can be viewed as delay-tolerant networking. Okay, so what is delay-tolerant networking? It's networking where there is no end-to-end path. So for example, I can have a memory stick in my pocket. This could be a memory stick I put it in my pocket. I walk over and give it to somebody else, and now they have the content. So let's say I have a movie and I want to give it to Kevin. I'll download the movie, put it in my pocket, walk over to him, give it to him, and now he has the movie. Okay. So in the same way, we can think of cars as carrying energy. They're what we call data mules, energy mules. So why am I showing cows and bees over here? So let me now kind of hypothesize 2 interesting systems. In the cow system, well, how do cows work? As a systems engineer, the way cows work is you send them out in the field, they graze, they make milk, they come into the collection center, and they deposit the milk, and then they go do it again, right? So imagine that I have a bunch of cars and a bunch of houses which all have solar cells. So the farmer who's getting the milk is actually a utility company that wants energy. So what happens is the cows go to the houses, fetch the solar energy into the cars, come back, and then the utility extracts the energy from them and uses it for whatever purpose they want. So we can actually collect energy in this fashion without having to have 2-way connection from the home to the grid. Okay. Remember, some of these renewable energy sources are in deserts and so on. So T. Boone Pickens couldn't bring grid supply all the way. Maybe you could have trucks with batteries or railroad cars which are actually carrying energy back, okay, from the windmills back to California. You could probably do that using the analogy over here. This one is a bit more far-fetched. That is a pun. So these are honeybees carrying pollen. So imagine you have a neighborhood or an apartment complex, and a lot of people have cars. And we know that the next day is going to be a hot day, and there's a possibility that you'll be asked to reduce your energy load. So you could tell all the people, look, go and gather pollen and bring it back. Go gather energy from your workplace or wherever, bring it back in. The next day you plug in your cars and you're fine. You can use energy in this fashion. So, okay, I grant you these are far-fetched, but the analogy is at least illuminating. Okay, that we can carry energy, we can swap it, we can make these delay-tolerant network algorithms used in the context of the smart grid. The third one I'll spend a little bit more time on, and this is kind of something that I worked on quite a lot some 20 years ago. And this is basically congestion control for the smart grid. So I call this load control. So every house, every building, pretty much every circuit has what's called a circuit breaker, which limits the amount of current flowing through. If you exceed the circuit breaker, if it's a 15 amp circuit breaker, if you exceed 15 amps, it trips and you get 0. It's exactly like a peak rate limiter with the funky behavior that if you exceed the peak rate, you get 0. Okay, it's a very harsh peak rate limiter in the network sense. Now, if you are going to exceed your current, or if you exceed the overall capacity in the core, what happens is a phenomenon called frequency droop, which means that instead of getting a frequency of 50 hertz, you're going to go to 49.5 hertz or 48.5 hertz, and that tells us that the network is congested. So in the internet today, what happens is that if you exceed the backbone or the core capacity, the core is free to drop packets, just drop packets, and then the sources will reduce their rates. Alternatively, sources can do reservation, say, I want this rate, and the network can say, no, I can't accommodate you. So can we use these ideas of proactive and reactive congestion control to change these circuit breakers? Instead of having these dumb circuit breakers, have these smart current regulators which say that, okay, I'm going to give you up to 20 amps. You can go, if you go at 20 amps, you'll get it. If you go above 20 amps, you will still only get 20 amps. Okay? And that makes it look a lot like a peak rate limiter. And then we can maybe apply principles of congestion control to do this. So let's see what it would look like. Here's a systems architecture I'm showing over here. So I'm showing the grid connected to substation. Remember, that's what I showed you earlier. And those are all the transmission poles connected to substation. And the substation goes to the smart circuit breaker to some meter into the home. So that's what I call the data flow over here. That's electricity. So there's electricity flow with these bold arrows going through over here. That's what we have already today, more or less, except I've introduced a smart circuit breaker. In addition, I'm going to introduce two control elements, a smart home controller, which could be nothing more than your broadband internet gateway, okay, your DSL modem or whatever you have at home, your firewall, for example. And this one is a new thing called the substation controller, just a computer sitting on the other end that talks to the smart home gateway and the smart circuit breaker. So what happens is that the substation controller is looking for congestion on the grid. When congestion happens, it sends a signal to the home controller saying, you need to slow down. Okay, exactly like what's called explicit congestion notification on the internet, where a router will send a bit on the header saying, look, you're using too much, reduce your rate. Okay, in the same way, the substation controller can send a message to the smart home controller saying, reduce your rate. What happens is the smart home controller talks to the home appliances and shuts them off by using, say, Zigbee control or a smart power strip or something like that. The nice thing is that this architecture, by mimicking the internet, is able to scale to millions of endpoints. We're not restricted to thousands of endpoints. You can do millions or even billions of endpoints using this. You just have frequency droop detection over here, and you can just send a message over here. And all this communication path over here is stuff that we really know how to do. Okay? So what do we really want to do here? Let me show you a picture of how this works. Let me show you how proactive control would work. So let us say we have two homes, this one here and this one here, and this is the profile. So what is it showing over here? On the x-axis is time, and the y-axis is the energy usage. And here is an appliance, let's say an air conditioner, which comes on at this point in time and this point in time. And then the other house, the air conditioner comes on twice at these 2 points in time. As you can see, at this point over here, which is in the middle, both are on at the same time. So the generation capacity need on the back end is sort of 2 units, okay, because they're overlapping. Now, the nice thing about an AC is that your room or your house has thermal mass, which means that if you don't cool it exactly at the right point in time, it's okay, because you're going to cool it a little bit later, a little bit earlier. You won't notice the difference. Okay, in this room, if the AC is turned off right now, you wouldn't probably know for about 5 minutes. So I can move these things around. So by moving this and this around, what happens is I can fit these loads into this load over here. At this point, the back end needs a generation capacity of just 1 rather than 2, which means you can turn off the coal plants, right? Because you don't need to have all the extra generation capacity over here. You don't need to build those coal plants even. Okay, so what I'm showing here is the ability for us to smart or effectively control the loads by doing bin packing, okay, or computational geometry, if you want to call it that, which allows us to schedule loads in such a way that we can actually save on electricity. So how well does this work? Okay, I'll show you a small graph just to illustrate the point. Assume that all the houses look the same, And we assume that they only have one peak period, and I'll call that some probability of being on. And if they're all, if they're uncorrelated, which means what is this today, these things come on at random periods of time, then I can model this as a binomial distribution because each of these is a Bernoulli process with some probability of being on, so the aggregate is a binomial. On the other hand, if I can schedule them just the right way using bin packing, then I get a deterministic schedule, okay? And it turns out to be relatively easy to compute what is the what is the amount of electricity used, the generation capacity you need for both of these cases. And this allows me to compute the following graph, which I'll show you, which shows the amount of gain, percentage gain, or percentage reduction in capacity you can get, okay? So here is a graph showing that. So on the y-axis, this axis over here is the fractional reduction in the peak capacity. So how much you can bring down the peak capacity depending on the number of homes and the fraction of time that they're on. So the dependence on number of homes is not that strict, but this is not linear over here. It's just a bunch of different points. This is a histogram, really. What is important is that in the range from about 10% to 75% fraction of being on, we get reductions about 20 to 50%, okay? Which means we can reduce the generation capacity by about 20 to 50% compared to what you have today without affecting anybody as long as you schedule loads properly. So this is what you can think of as the gain from scheduling. So I'm really happy with this approach. It shows that you have, even if I'm off by a factor of 2, you can still get 5 to 10%, but even 5% is a few $100 billion, okay? In the grand scheme of things, it's a lot of money. So how are we getting this gain? We're getting this gain by using our ideas of scheduling, okay, and proactive congestion control. So we can take that whole body of work, put it over here, get those millions of points of control using essentially internet technology, and in fact alter the way the grid actually works. That's what I mean by fundamentally changing the structure of the grid using ideas from internet. And to me, this is far more exciting than just turning off the routers when not being used. All right, I'll show you a small slide on reactive control. So here I'm showing you how TCP works. You have two sources. They both start off and keep going up. You get a congestion signal, you go down. And you keep doing that. Eventually, they both look the same. Imagine I'm doing this with air conditioners. So I start off by having the air conditioner on for 1 minute out of 5. And if nobody complains, I keep increasing it until at some point you have frequency droop and both sources go down. But as you can see, they eventually converge. And we can use the same idea of explicit signals coming back from the substation to actually control the duty cycle of thermal loads, of air conditioners, clothes dryers, etc., which you won't even notice, actually, okay, for the most part. Now, in order for all this to work, the many open problems, I will not ask you to read all of them. Suffice it to say, there's many different things to work on for the next 5 years, because this is just a high-level concept. You really need to translate that into practice. So to conclude then, I believe that the next 10 years, maybe next 15 years, will decide the grid of 2120. I'm actually extremely confident in this prediction because I'm not going to be here in 2120 to see whether it's true or not, and neither are you. So it doesn't really matter what I say. Okay. However, the other part is that the internet is sort of kind of like the grid. Look at it sideways in the in the dark corner. If you don't pay too much attention, it sort of looks the same. And therefore, we can use the last 40 years of internet research. We should. It may help. And if it is, it will be a rich area for very impactful research. I think that we can have a chance to not only avert the grid from the kind of collapse that you've seen, cascading problems that you've seen in the past, but also make it greener and more useful for everybody. And with that, I'll leave up this slide over here, which is our website, the ISS FURI Information Systems and Science for Energy website, which has an overview paper describing this work in a bit more details of our projects. And there's a lot of online resources and data sets of wind and solar and electricity prices. And you can see solar generation and all sorts of stuff that we found, the Danish windmill production, anything we get our hands on, we put a link to it. So, please feel free to take a look. And with that, I'll pause for, stop and take any questions. Thank you.
Questions at the remote site.
Okay, are there any questions from the remote site?
Yes, in the Do you anticipate houses having demand schedules that are transmitted to substations or things like that? Or is it all just sensing what's being done?
Right. So we anticipate that. So the houses already have the ability to. Any house with broadband already has the ability to do computing and the ability to communicate. Okay. Now, how should we use this? There are many different possibilities. One possibility is what you suggest. The houses create, based on past history, a prediction of the demand that they need for the next scheduling period. Let's say the next 5 minutes. And then the network says, yes, you can have it, or no, you need to reduce some of it. And then the house controller decides what to reduce. Okay, it's very much like admission control in the internet. Or not in the internet, but admission control that was studied in the context of the internet. It never got implemented. But we certainly know how to do it. Does that answer your question?
Yes, that's fine, thanks.
Okay, thank you. Any other questions from the remote sites?
I have a comment, Keshav.
Yeah.
So, as you mentioned, I mean, we discussed this in person, but I thought I'd have you admit it in the talk as well, about the importance of the autonomy of the participants involved in the ultimate success or failure of the vision. So, in other words, you cannot have a situation where you can go in and unilaterally move people's loads around earlier or later, but you have to have a system of incentives where the participants themselves are willing to do that or want to do that in some shape.
Yes, that's correct. I mean, whenever we have control schemes and people are paying for service, obviously they have a say in what they're getting. And so there has to be incentivization of one of the problems I put up there. So these load control schemes have to be combined with appropriate incentive schemes. Now, I should add that, by the way, the internet has no such incentive schemes. If you send too many packets into the internet, it's just dropped. You don't have any control over that, yet you seem happy to use it, right? So we could have a similar situation over here if that was required. It's not obvious that you must always have an incentive scheme. We certainly don't have one in the internet.
Can you comment, a question, NC State, can you comment on any pilot projects that may be running right now with this with schemes like you described, so we can get some hands-on data or experience?
We certainly are not running any pilots at the moment. Most of our pilots right now are in measurement because we want to understand the problem before we can try modeling it. However, a direct load control where the grid controls appliances directly has been tried. There's something called the Grid-Friendly Appliance Forum, which is, you can go look it up. And in fact, I think Whirlpool has said that they'll manufacture 1 million grid-friendly appliances by the end of 2011. So the technology for doing that is there. It's being put into place. The problem with the Whirlpool appliance, of course, is that nobody knows how to control them exactly. And some trials of direct load control where homeowners where appliances are controlled by the grid turned out very negatively. Homeowners didn't want that. Okay, they wanted to have some say in when things were turned off and turned on. So the jury is still out about how exactly it needs to be done. In my own personal opinion, there has to be some kind of human interface for the grid, some computer-human interface work where people are able to express what they want and the grid expresses what it wants. There's a negotiation going on. Without that, it's going to be very difficult for people to swallow direct control. The place where it might work would be for hybrid cars. If you plug in your car, then you don't really know how much it's. You just see a green light. You don't know whether it's charging or not. It says it's charging. You could actually have direct control of the charging rate increasing and decreasing over time in response to the grid condition without the owner necessarily being aware of it or even caring. Okay, as long as it charges by the end of the night, they don't really care when it was charged. And so some of these regulations, fine-grained regulation, might be best suited for the cars.
A devil's advocate here. If I have a car that I bought with expensive batteries,
yes,
and I may have read consumer reports that the batteries would last very long if I treat them in some fashion that I control. One day, if they are just discharged and charged and discharged according to the demand on the network, my car batteries won't last.
That's correct. I mean,
I'm not happy.
So again, this is a question of incentives. You know, it could be that if you were to, if you don't charge and discharge a car battery properly, it can reduce the lifetime. That's well known. Okay, so first of all, you have to be pretty smart about how you charge and discharge it, and those are actually fairly well-known algorithms. So obviously, you don't want to do something very stupid about that in terms of how you charge and discharge. But the second point is that if you're being compensated monetarily for that, then maybe you don't care. Maybe it brings down the lifetime by a few days a year, but you're making a few $1,000s for that, so maybe you don't care. You know, it's all a question of risk and reward. But it has to be compatible in terms of what users want and what they get. Any other questions? The remote? Yeah, okay, local questions here? Yes.
Could you elaborate a little more on the energy mules? Because it sounded like you were going to have Waterloo have you drive the car so that you could power the university during the day, but that's when your house is generating the electricity.
Well, this thing over here, the cows are gathering wind energy, perhaps, which blows at night more strongly than by day. Since it's all, you know, let's say castles in the air, I can change the story as I see fit. Yes.
So, I mean, all of this, what can probably be called statistical multiplexing gains make a lot of sense. But this whole point about storing energy in cars and driving them like the Texas billionaire you were talking about,
yeah.
Is it really cheaper to have trucks transport the energy and batteries on their back rather than do it through lines?
No, it's not. You're much better off transmitting lines. However, you know, the question is, if you can get the rights of way, then it's better to do it that way. But if you don't have rights of way, you're forced to use the railway lines, you're forced to use a road transportation network, this may be an alternative. You know, the point is more that the delay-tolerant networking research may have some application over here, rather than any specific scheme. So I'm kind of pointing to this big thing. You can find problems with everything that I say because it's a very high-level thing. But the idea is to use those concepts. Can they be used? Can they be applied over here? At this stage, all I can say, yeah, my gut instinct says it's possible. Now, we don't have those cars in production yet. We don't know how easy it is to remove and put the batteries back in. A Better Place is trying to do it. They claim they can have robots that can actually go in and take a battery, put in a new battery, do that all in about 2 or 3 minutes. So yes, maybe it's possible. We don't really know for sure. We don't even know if people want to have the batteries taken out, okay, and replaced, because you know, the charge-discharge behavior of these batteries, you don't know when you get from somebody else's battery. Maybe they were not driving properly, okay, or maybe they didn't treat the batteries well, and so you're getting something bad instead of your good stuff, right? So all of these issues are still unresolved. But it's just a very high-level line of work. Yeah. The other two problems are a bit more grounded, I should say. This one and the third one are quite a bit more grounded. Any other? Yes, Kevin.
So, as you know, the control problem on the internet is fundamentally driven by the notion of round trip time, of the basic delay in the control loop. So what sorts of timescales are you envisioning here for the adaptations?
So the control time loop over here is basically over here, from here to here, right? So the communication delay actually is not it's not difficult. That's pretty easy to do, okay? In other words, the round trip time from the substation to the smart home controller is probably under a millisecond for most situations, because the substations are fairly close by, under 20 kilometers. Okay. In terms of sensing and yeah, right. So that's where it gets interesting, because the home appliances that you're going to turn on and off have some intrinsic limits. Okay, so typically, for example, a fridge, when you turn it on, you know, the paper's research indicates it needs to be on for 7.5 minutes or so, 8 minutes, let us say. If you turn the AC on, it should be kept on for 15 minutes or so, otherwise the compressor lifetime degrades. So the time scales of control are about roughly 10 minutes to 20 minutes, I would say. So the communication round trip time is not the problem. It's the physical response time of the underlying appliances that's the problem. Any other questions from you? Yes?
The bin packing problem you described.
Yes.
That's if you solve the whole problem locally at the substation.
Yes.
And the residences it serves. But you're also free to request a little bit more from the grid.
Yes.
At greater expense.
Right.
So how to manage that trade-off?
That's a great research proposal. You know, I should apply for funding. No, I mean, I don't know. I really don't know. In fact, I don't even know whether we should do bin packing here and send the packed bin here and do two-level scheduling, or just have the raw information set over here and do scheduling over here. This makes the problem larger, but maybe you get more gains, right? So we don't know. Okay. Also, the actual profiles don't look like this. They don't look like squares. Okay. We have seen, we've collected traces of home electricity usage over every 6 seconds, okay, over a period of about 5 or 6 days from a particular home, and it doesn't look like this at all. It's kind of flat, and then there's spikes. There are definite spikes, very, very sharp spikes going up and down. That's your microwave turning on and off, for example. Okay, it's your kettle going on and off. So how do we deal with those spikes? It's not clear it's a good bin packing problem, but at the right time scale, it'll be a bin packing problem. So we need to figure that out.
So do you envision a future where we press the button for the light and 5 or 10 seconds later it comes on, or you put toast in a toaster and it says not now?
So the short answer is it's already happening in Sweden. So I just heard from somebody, they had gone to Sweden and they had a clothes dryer and they had another thing, I forget what it was. It was, I think, the two appliances, okay? And they pressed the button, it wouldn't come on. So they said something is wrong. They called up the grid people, the electric people. They said, oh yeah, it'll come on at 6 o'clock. Okay, so they don't let you dry your clothes before 6 in that particular part of Sweden because they don't want you to. And you can complain all you want, but what are you going to do about it other than put your own diesel genset, okay, which you may not want to do. So some of these rules may be imposed in order to meet whatever requirements there are from the back end. Okay. Do you want to put in another $4 or $5 billion plant, or do you want to have consumers suffer a little bit of pain by not drying their clothes at 4, but to do it at 6? It's a societal trade-off. Some societies will say it doesn't matter. We're going to drive our Humvees and we're going to dry our clothes at 4 in the afternoon, and that's what we want to do. Okay, and other societies may decide differently. Yeah. Any other questions?
Great.
Okay.
Well, thank you again, Keshav.
Okay. Thank you.